In this video, I want to introduce a new practical method for checking the 25% lateral force resisting requirement for moment frames in dual systems using ETABS. This workflow allows us to evaluate the moment frame contribution without damaging the gravity load behavior of the shear walls. And the best part is, everything can be performed inside the main analytical model. In structural engineering practice, several methods are commonly used to verify the 25% lateral load participation of moment frames in dual systems. Many engineers remove shear walls, modify stiffness values, or change cracking factors. However, all of these methods usually introduce secondary modeling problems. The biggest issue is this: when shear walls are removed from the model, their gravity load participation also disappears. But according to the design philosophy of international seismic standards, the intention is only to eliminate their contribution to lateral resistance, not their gravity load behavior. For example, removing walls completely may affect stiffness distribution. Cracked section modifiers may unintentionally change vertical behavior, and simplified approaches may distort force transfer paths. So in this tutorial, I want to show a cleaner and more stable alternative method. A method that keeps gravity behavior, diaphragm action, and realistic structural interaction while removing wall participation only from lateral resistance. This idea is closely related to the philosophy of international standards such as SC7, the CI 318. FEMA seismic modeling recommendations. The core concept of dual systems is, meaning the moment frame system must independently resist at least 25% of the design seismic base shear. Important note, the objective is not to remove gravity participation of shear walls, but only to prevent them from resisting lateral seismic forces during this verification stage. Now let's move into ETABS. Here I have a very simple symmetric dual system model, created only to demonstrate the workflow. The shear walls are already grouped inside ETABS. If we go to Define Gives Groups, you can see a group named WALL. This group contains only the shear walls that participate as the primary lateral force resisting system. The key idea of this method is using nonlinear staged construction analysis, even though the structure itself may remain essentially linear. The staged analysis feature allows us to selectively remove structural participation during specific loading stages. This is the important engineering trick. Instead of modifying stiffness, we temporarily remove the wall structures only during seismic loading stages. That means walls remain active for gravity loads, but become inactive for lateral seismic resistance. Inside Define Gives Load cases, I created a nonlinear static staged construction case. In this example, nonlinear material hinges and advanced nonlinear parameters are not necessary, so all nonlinear options remain disabled. The default ETABS settings are sufficient for this workflow. Inside the staged construction case, I define two stages. Stage 1, add structure, here. The entire structure is activated, including frames, slabs, columns, and shear walls. Stage 2, remove structure, here. The wall group is removed from the model. This means the shear walls no longer participate during the seismic loading stage. Now we define the seismic load case, for example, X or EY. Inside the seismic load definition, we activate Use Nonlinear case and select the staged construction case as the initial condition. So ETABS starts the seismic analysis from the final state of the no wall stage. This is the key step of the entire method. Now the behavior becomes very interesting. During dead load, live load, the shear walls still exist. So gravity stiffness, gravity force transfer, and diaphragm interaction all remain completely realistic. However, during the earthquake loading stage, the walls no longer participate in lateral resistance. So the seismic forces are redistributed primarily into the moment frames. Let's verify the behavior. If we display deformed shape under dead load, we can clearly see the walls are active. Stiffness participation is normal, and gravity behavior remains unchanged. Moments, shears, and gravity force pads are all behaving normally. But if we display deformed shape and array, we immediately notice something different. The walls are now absent from lateral participation. The columns and moment frames are carrying the seismic response. The diaphragm still connects the system. So lateral force transfer remains stable and realistic. To confirm this behavior, we can check. Display gives show tables gives base reactions for X or A. We can see the total seismic base shear carried by the remaining frame system. For example, approximately 84.6 tons, which can later be compared against the required 25% criterion. If we activate shear force display and cut a section through the structure, we can clearly observe that seismic shear forces are now transferred directly into the columns and moment frames, while the walls are excluded from lateral resistance. This confirms the correctness of the staged construction workflow. So in summary, this method provides a very clean and efficient way to verify the 25% frame participation requirements in ETABS without removing walls from gravity behavior, modifying stiffness artificially, or creating unstable secondary models. It is a practical and powerful workflow for dual system seismic design.